Welcome to week 4, Probability and Statistics for Machine Learning. Day 1, we'll be looking at probability theory and random variables. Day 2, we will be covering probability distributions in machine learning. Day 3, we'll be looking at statistical inference, estimation, and confidence intervals. Day 4, we'll be looking at hypothesis testing and p values. Day 5 will cover types of hypothesis tests. And on day 6, we'll be looking at correlation and regression analysis. Followed by day 7, where we'll be doing our statistical analysis project, where we'll be analyzing some real world data. So let's get started with week 4. Welcome to week 4 of day 1, where we're going to talk about probability theory and random variables. First, let's get into some of the basic probability concepts. We have sample space and events, where sample space S is represented as the set of all possible outcomes of a random experiment. Example in this case can be a rolling a die. The S or the sample space in this case is 1, 2, 3, 4, 5, 6 because those are the 6 different combinations that are possible or possible outcomes. Then we have events. Events is a subset of the sample space. Example can be rolling an even number where e equal to 2, 4 or 6. So those are the possible outcomes, which is an event that might happen, or rolling an odd number, in which case we have 1, 3 and 5. Next, let's talk about conditional probability. The probability of an event A occurring given that B has occurred. We saw this something in the last week in one of the classes. Example here can be rolling a number greater than 3 given that it is even. Next, we have independence. Two events A and B are independent if P A union B is equal to P of A times P of B. Example in this case is the outcome of two separate coin tosses. So let's look at this example using Python. So I'm going to create a new file, save it inside my day 1 of week 4, call it sample, and in here I'm going to use a library called as iter-tools or iteration tools. I'm going to import from this product. Now I am going to go ahead and set a sample space of a dice roll. Here I'm going to say sample space equal to list range from 1 to 7, which is 1, 2, 3, 4, 5, 6. These are the different options that we are going to create a list of. Now let's look at the probability of rolling an even number. So I'm going to say even numbers are, what are the options? We have 2, 4 and 6. These are the 3 even numbers. I can say probability of even equal to length of even numbers divided by length of sample space. And I'm going to say print, in this particular case, P even is probability of even. Let's save it and let's go ahead and run this. Clear Python day 1 dot sample, and the probability of even is 0.5, which is 50%, which is true because there are 6 numbers and getting one of the even numbers is half the percent. So that's perfect. Next, let's look at random variables. Now, what are random variables? A random variable maps outcomes of an random experiment to numerical values. There are two different types. One is a discrete and one is continuous. The discrete takes a countable number of values, example, number of heads in 3 coin tosses. And continuous takes values from a continuous range, example can be height or weight. We also have probability mass function. which is always spoke about as PMF, and we've used some of these functions earlier last week. Now this describes the probability distribution of a discrete random variable. Example can be rolling a die, where the probability is 1 by 6 because there are 6 different spaces there. Let's talk about probability density function, or PDF. This describes the probability distribution of a continuous random variable, which is weight or height. Next, let's talk about expectation, variance, and standard deviation. Now, expectation, E of x, is the weighted average of a random variable's possible values. E of x can be calculated as summation of ranges of x, x times p of x equal to x, which is discrete, and E of x integral from minus infinity to infinity x times f of x dx for continuous. We also have variance, where x measures the spread of a random variable. Variance x equal to E of x minus E of x square. We have next standard deviation, sigma of x. The square root of variance is standard deviation. So that's why sigma of x is denoted as square root of variance of x. Let's look at some examples in Python. So first, here I'm going to remove this, and for our example, we are going to import numpy because we've used this last week, some of it. So probably if you remember some of those, it would be helpful. But I'm going to say random variable. In our case, let's take a dice roll. And here I am going to first put down the outcomes. The outcomes can be an array of items 1, 2, 3, 4, 5, and 6. These are the outcomes of a dice roll. Next, let's say probabilities equal to np.array is 1 divided by 6 times 6, because there are 6 different outcomes. Next, I am going to say expectation. For expectation calculation, as we saw the formula, it's np dot sum of outcomes times probabilities. That's our expectations. We can print it out. Expectation, which is also mean, is expectation. Next, let's calculate the variance and standard deviation. Now that variance I can calculate as np dot sum of outcomes minus expectation squared, which is star star 2 times probabilities. So that will give us variance. And standard deviation, as I mentioned, that's the square root of variance. So let's print these out. Variance is variance, and standard deviation will be std def. Perfect. Let's run this, clear it out, and there you go. Expectation or mean is 3.5, variance is 2.9, and standard deviation is 1.707. So let's go ahead, and now that we know how to do expectation, variance, and standard deviation, let's jump into hands-on exercise. Our first exercise today will be to simulate dice rolls and calculate the probabilities. The objective is to simulate dice rolls and calculate probabilities of different events. So what we will be doing is we'll be simulating rolling a die 10,000 times using Python and calculate probabilities of rolling an even number, a number greater than 4, etc. So let's go ahead and start with our code. I am going to clear this out. Go here, create a new file, save it as day1 underscore exercise1.py. Now let's start with importing numpy as np, and you heard me right, we will be simulating 10,000 dice rolls. How do we do that? Rolls equal to np dot random int, since I want integers from 1 to 6, say 1 to 7 because it excludes 7, size equal to 10,000. There you go. Perfect. So this will give me rolls of 10,000. Next, let's calculate probabilities. First, I'll say to get an even number, as I mentioned, we want to see probability of it being even. I'm going to say np dot sum rolls mod 2 equal to 0 and divide that by length of rolls. So there you go, that's 10,000. Next, I'm going to say p. Let's say if we're checking if greater than 4, what are the possibility? Np dot sum rolls is greater than 4, again divide by length of rolls. So we have greater than 4, we have only two options, 5 and 6. This one has 3, so the probability of even should be more than probability of this. So let's go ahead and print it out. P of even is P of even, and then print probability of greater than 4 is P underscore greater than 4. So let's look at the results. Python day 1 exercise 1, and there you go. For probability for even is 0.05, which is almost half the percent, but based on the numbers it looks like 0.5051, which is more than 5.5. So the rolls had more even numbers than odd numbers, whereas greater than 4 has 0.33, which makes sense because there's only two numbers left, which is 1/3 of the total numbers. So perfect. So that worked perfectly for us. I hope you were able to walk through this exercise. Our next exercise, let's save it as day1 underscore ex2.py. But what is it? Our second exercise is to create and analyze random numbers. The objective is to create discrete and continuous random variables and analyze them. So we will be creating a discrete random variable representing the outcomes of a die roll. Next, we are going to create a continuous random variable representing a uniform distribution between 0 and 1. So let's go ahead and try to write this code and also plot it out. So I am going to, since we are going to plot it out, I am going to import matplotlib dot pyplot as plt. Next, for uniform distribution, I am going to use the library from stats and import the function uniform. So that's available there for uniform distribution. So our first step is to get a discrete random variable, which in our case is a dice roll. Now to do this, I'll put down the outcomes again, equal to, as you know, 1, 2, 3, 4, 5, and 6. Next, let's get the probabilities. Probabilities equal to 1 divided by 6 times 6. Next, let's plot a bar diagram where we can show the outcomes, probabilities, and then let's give a color also. equal to, let's start with blue, and if you want to give some transparency, alpha equal to 0.7, so it's not too bright on the eyes. I'm going to give a title to this, and this title I am going to say PMF of a die of a dice roll. Next I'm going to say plt.xlabel. For x label, we were using outcomes, so that's what I'm going to specify here. For y label, we are using probability. That's what we're going to display here. And let's say plt.show. So let's do half of this first and then look at how it looks like. I'm going to go here. I am going to say Python day1 underscore ex2 and run it, and there you go. The outcomes are pretty consistent, 1 2 3 4 5 6, so the probability is equal for any of them to show up, even though the numbers might be a little different, but it will always be the same, equal amount of probability. Now next I want to comment this out, and next let's do a continuous, let's see, continuous random variable uniform distribution is what I will be using. Here I am going to say x equal to np dot linspace, and to this I'll give 0, 1 and 100, and then pdf I will say uniform dot pdf and use x. I'm going to use a log of 0 and I'll use a scale of 1. Next let's plot plt dot plot. I'll pass x, pdf, color equal to, let's make it red, not going to give any alpha. I'm going to say plot dot title. Let's give a title to it, and title we can call it pdf of uniform 0 to 1 plot dot x label. For x label we are using x, and plot dot y label we are using the function f of x. Next let's show it, save it, run it. Actually let's close this one, clear it out, run it, and it says there's an error np because we forgot to import numpy as np. Let's run it again, and there you go. We have a uniform 0 to 1. We have a uniform line here which shows the representation between x and f of x. So that's kind of confirms our discrete and continuous random variable generation. Now next, if you want to do some more additional practice, you can start with simulate flipping a coin 10,000 times and calculate probabilities of heads and tails. Next, you can also compute the expectation and variance of a weighted die and use biased probabilities, and explore other distributions. We just did the uniform distribution, but you can look at normal, binomial, and use Python for it. So just to summarize, today we dived into foundational probability concepts, random variables, and their statistical properties. By simulating experiments and visualizing distributions, we gained practical insights into probability theory and its application in machine learning. So if you have any questions or problems or have any issues, let me know and I can get back to you. Day 2, probability distributions in machine learning. Some of the things that we're going to cover today have been already covered in the previous videos, but this is more focused towards the distributions that we'll be using in machine learning. So we'll start with common probability distributions. We have Gaussian distribution or normal distribution. This is a bell-shaped curve characterized by mean, which is mu, and standard deviation, which is sigma. Probability density function for this PDF is defined as f of x equal to 1 divided by square root of 2 pi sigma square e raised to minus x minus mu square divided by 2 sigma square. The properties include it's symmetrical about the mean, and mean, median, and mode are the same for this. Applications in ML include its common assumption in many algorithms, example, naive Bayes, and used in feature scaling, example, standardization. Then we have the binomial distribution. Models the number of successes in n independent Bernoulli trials. It follows the probability mass function PMF, which is defined as P of x equal to k equal to n to k, P of raised to k 1 minus P raised to n minus k. The properties include its discrete distribution. Parameters are n, which is number of trials, and p, which is probability of success. Its application in ML include logistic regression, assumes a binomial distribution for binary classification. Next, we have Poisson distribution. It models the number of events in a fixed interval. The PMF or probability mass function is defined as P of x equal to k equal to lambda raised to k e raised to minus lambda divided by k factorial. The properties include its discrete distribution, and the parameter is lambda, which is average rate of occurrence. It has some applications in ML, including used in event modeling. Example can be clicks on a website. Next, let's look at uniform distribution. This is equal probability for all outcomes in a range. The PDF or probability density function is defined as f of x equal to 1 upon b minus a, where x is part of a to b. Properties include continuous distribution, and parameters are a, which is the lower bound, and b, which is the upper bound. Application in ML include random initialization of weights in neural networks. Next, let's look at application of distributions in machine learning. So Gaussian distribution, which we discussed, is used in algorithms like naive Bayes and Gaussian mixture models. It's assumed in statistical tests. Binomial distribution, on the other hand, is foundational for logistic regression and other binary classification models. We have Poisson distribution, which is applied in modeling count data, example customer arrivals. And then finally, the uniform distribution is commonly used in random sampling and initialization of parameters. Let's look at visualizing distributions and understanding their properties. Now, visualization helps understand skewness, kurtosis, and outliers. Skewness is the measure of symmetry. There's positive skew or negative skew. Positive skew is tail on the right, and negative skew is tail on the left. Kurtosis, on the other hand, is measure of tailedness of the distribution. It has high kurtosis or low kurtosis. High kurtosis is more outliers, and low kurtosis symbolizes fewer outliers. Let's look at an example for this in using Python. So I'm going to go ahead, start a new file, save it as day2 underscore samples. And here first, let's import some of our libraries. I'm going to say numpy as np. Then for plotting, let's import matplotlib.pyplot as plt. Next, from scipy.stats, we'll import all the algorithms: normal distribution, we spoke about binomial distribution, Poisson distribution, and uniform distribution. So let's import all of them. Next, let's start with Gaussian or normal distribution. The way it starts is, let's create an x variable, np dot, let's add some data inside it, linspace, and for this I'll give -4 to 4 with 100, and then plot this plt dot plot x comma normal dot pdf, and here I can put x comma lock equal to 0 comma scale equal to 1, and then I'll also give label here directly so we don't have to do multiple lines, and say Gaussian mu equal to 0 and sigma equal to 1. So there you go, that's our Gaussian distribution. Let's do binomial distribution next. For this, we'll use n and p, there's two different factors as we mentioned. Assign values 10 and 0.5. Next, we'll say x equal to np dot range and give it 0 comma n plus 1 values, and let's plot a bar graph for this, and I'm going to say x comma binom dot pmf and pass it x comma n comma p. These are three things that needs, and then I'll say alpha equal to 0.7, so it stands out a little bit from the other. Label equal to binomial, where the values can be n equal to 10 and p equal to 0.5. So that's our binomial distribution. Now next, let's do Poisson distribution, and for Poisson distribution we will start with LAM equal to 3. We need x equal to np dot range, give 0 to 10, and we'll plot a bar for this. We'll pass x Poisson dot pmf and pass x comma lam. Alpha I'll give as 0.7. Label equal to, let's call it Poisson with lambda equal to 3. I think I closed it earlier a little here. Close this here. Perfect. Now let's say plot dot title and call it probability distributions plt dot legend, and then show all of them together. Save it, go here, run my Python day2.samples, and there you go. We have our Gaussian, we have our binomial, we have our Poisson, Gaussian, binomial, and Poisson, all of them in one single graph displayed here with their values displayed right here. So I hope you were able to do this visualization, because that's one of the important things that we would be using once in machine learning, specifically when you have to prove things or do show based on data how the flow looks like. It's much more helpful to do visualizations. I'm going to close this, clear it out, go back here, save it, go back, and next let's jump into our hands-on exercise. Exercise 1 is to plot and explore various distribution. The objective here is to visualize and analyze key properties of distributions. What we will be doing here, we'll be plotting Gaussian, binomial, Poisson, and uniform distributions and observe the effect of varying parameters. So what I'm going to do is, since we already did part of it earlier where we displayed everything together, the only thing that we forgot to do, even though we have uniform here, so I'm going to go ahead and also do the uniform distribution here. I am going to use for this x equal to np dot random dot uniform, and then I'll say low equal to 0. It needs low and high equal to 10, and it also needs the size of the data. I'm going to say 1000. So that's what will be created randomly for us. SNS dot hist plot where will give x comma kde equal to true, will give label equal to uniform, and color will give red in this case, and let's of this rest of stuff should be same. So save it and go back and run it again. Oh, we don't have SNS here, so I am going to say import Seaborn as SNS. So that's doesn't give me an error. Let's go ahead and run it again, and there you go. We have our Gaussian binomial, Poisson, and uniform, which is laying on top of everything right here. If I remove this, it probably show me just the other stuff, but this looks good for us, showing the probability distribution from 0 to 10. There you go. And that kind of covers our exercise 1. Our second exercise is to analyze a data set's distribution. So the objective here is to analyze the skewness and kurtosis of a data set. We'll load a sample data set, example iris, which we have used earlier in first week or second week, and we'll calculate and visualize the skewness and kurtosis of a particular feature. So what I'm going to do is I am going to start with a new project, and I'll call it day2 underscore exercise.py. I'm going to get the URL. This is the URL that we'll be using. So I am going to take this here, keep it here for now. And first I'll get my skypy.stats import skew and kurtosis. So these are two things that I need to check the distribution of the data set. Next, I need import pandas as PD to get my data set or data frame, and then next I'll import Seaborn as SNS for graphing that. So next, let's load the data set. I have my URL from this. Next, I am going to get my data frame using pandas.read. It's a CSV file, so I'm going to say read CSV and give the URL here. Perfect. Next, I'm going to analyze. So this is iris database, so it has sepal length, sepal width, a bunch of those things about flowers. So I am going to analyze one of them. Let's take sepal length from there. You can open this URL and check it out. You'll see what I'm talking about. The feature that I want to play around with is, as I mentioned, sepal length. That's what I'm gonna specify. Let's put it in double quotes. Okay, so sepal length. Next, I am going to say print the skewness is, we never calculated it, but you can directly calculate here. You can say skew, and inside that give the feature. Similarly, for kurtosis, I can do the same thing. Kurtosis, I can say kurtosis of feature. That will give me kurtosis for this feature. Now we want to visualize this. For that, I will say SNS dot heat plot, and this plot I'll pass feature as the first parameter, and KDE I will set it to true. Next, I am going to say PLT plot.title equal to is distribution of sepal length, and then finally I'll say just show the plot. So save this, and I am going to say python day2.ex. Let's hope it works. Underscore ex.py, and it says there is a problem with my heat plot. Oh, sorry, hist plot. clear it out, run it again, and it says PLT because I have not imported matplotlib. Plotlib.py plot as PLT. Perfect. So that should take care of all the errors. I'm going to go and clear it out, run it now, and there you go. It gives me the values of skewness or kurtosis and also displays them inside my graph here nicely, and I can check here the skewness and kurtosis values with a visualization of the feature distribution properly. So if you had something similar, that's good. If not, let me know in the comments or message and I'll get back to you. If you have any issues or if you have suggestions, let me know. For additional practice, you can compare the effect of skewness and kurtosis on different data sets. You can simulate random variables from custom distributions. Example, you can use a truncated normal, and also you can explore data sets with real world applications of distributions. Example, you can use stock prices for that. So just to summarize, today we learned the foundational probability distributions used in machine learning, their applications, and how to visualize them. By analyzing these real data sets, you can gain a deeper understanding of the significance of distributions in modeling and pre-processing data, which is a key step in AI projects. So I hope you were able to follow along and understand. If you have any questions, let me know. Day 3, Statistical Inference, Estimation and Confidence Intervals. Today, we're going to first look at Introduction to Statistical Inference. Now, what is statistical inference? The process of making conclusions about a population based on sample data. Now, what is population versus sample? Population is the entire set of individuals or observations, whereas sample is a subset of the population used to infer properties of the population. The goal is to estimate population parameters, example, mean, proportion, and assess the reliability of these estimates. Let's look at point estimation and interval estimation. Point estimation is a single value estimate of a population parameter. Examples include mean, which is an estimate of the population mean, mu, proportion, which is an estimate of population proportion. Next, interval estimation. This provides a range of values, which is confidence interval, within which the population parameter is likely to lie. Confidence interval formula is shown as Ci equal to x bar plus or minus z times s divided by square root of n, where x bar is the sample mean, z is the z-score corresponding to the confidence level, example 1.96 for 95% of Ci, s is the sample standard deviation, and n is the sample size. Let's dive into constructing confidence intervals. For means, when the population standard deviation sigma is unknown, Ci is x bar plus or minus t times s divided by square root of n. Use the t distribution for small samples where n is less than 30. For proportions, Ci equal to p cap plus or minus z square root of p cap 1 minus p cap divided by n. The p cap is the sample proportion. Let's look at this example with Python. So I'm going to create a new file, save it inside day 3 as day3 underscore sample. Here I am going to import numpy as np. Next, from skipy dot stats, I will import norm and t. So it's available there. Next, let's get the sample data first. So data, let's write some sample numbers: 12, 14, 15, 16, 17, 18, and 19. So I have my data. Next, I am going to calculate mean and standard deviation. To do that, I'm going to say mean equal to np dot mean and pass the data to it. Next, to get the standard deviation, I'm going to say np dot std and pass the data. And it needs one more thing, which is DDOF equal to 1. Now this DDOF equal to 1 is for sample standard deviation. Now next, I want to get the 95% confidence interval using t-distribution. Now this function we have imported from skykit stats. So skykit stats. So I am going to say n equal to length of data, get the data length, t underscore value equal to t dot ppf. This is the function we call 0.975 95% of the CI df equal to n minus 1. Provide that as t value. Now once I get that, I can get the margin of error equal to t value times standard deviation divided by np dot square root of n from our formula. Next, I can get the CI, which is mean minus margin of error, comma, mean plus margin of error. So I get the mean, and then I can add and subtract margin of error, minus and plus margin of error to see what my CI is. So let's print it out, which is 95% confidence interval, comma, CI. So let's see how does it look like. I'm going to open my terminal and say Python day 3, and there you go. Our confidence level is 13.62 to 18.06 based on the data that we have, which is pretty good considering the data sample size that you see here. Perfect. Next, now that we have all these in place, let's look at our hands-on exercise. Our first exercise today is to calculate the confidence intervals for sample data. Something that we just did is similar to that, but the objective here is to compute confidence intervals for the mean and proportion of a data set. So what we will be doing is we'll be generating a random sample data this time, and we'll compute the 95% CI for the sample mean. So let's go ahead and clear this out. I'm going to start with a new project, day 3 underscore exercise 1. And here I am going to first say import numpy as np. Of course, it's not going to work because I have not set up as py, so it will not show me my formatting. So I'm going to do again. Okay, import numpy as np. Next, I'm going to say from sky p py dot stats. I want to import norm, which is normal distribution. First, I am going to generate random sample data, as I mentioned. For data set, I'm going to say data equal to np dot random dot normal loc equal to, let's set it to 50, scale, let's do it to 10, and then size, we'll say we want 100 data points. Perfect. Next, let's do some sample statistics. So for that, I want to get mean equal to np dot mean of the data. Perfect. Next, I want to get the standard deviation, which is np dot std of data, comma ddof of 1. So sample standard deviation we get here, and n equal to length of data, which we'll be using in a minute. Next, to get our 95% confidence interval, first we'll get the z value equal to norm dot ppf of 0.975, which is our z score for 95% CI. Next, I'm going to get the margin of error, which is z value times standard deviation divided by np dot square root of n. So once I have my margin of error, I know my CI equal to mean minus margin of error, comma, mean plus margin of error. There you go. So that will give me my CI. Let's print these data out. I want my sample mean first, which is mean, and then I will display my 95% confidence interval, which is CI. Perfect. So that kind of concludes our exercise 1. Let's go ahead and run it. Say Python day 3 exercise 1. And there you go. Our sample mean is 50.56 based on the data that was uniformly generated here. Next, we have our 95% confidence interval is between 48 and 52. So based on the data that we have created, location is 50. We said that around 50. That's why it gave us mean of 50 and the confidence is 48 to 52. Perfect. That sounds good and right. So if you were able to follow along, that's good. If you can change your numbers and parameters and play around with it. Of course, every time you run it, it might give you a different value because I am not setting the seed for my randomizer. So I'm going to clear this out and look at our exercise 2. Our exercise 2 is to conduct sampling and create a report. The objective here is to conduct random sampling from a dataset, estimate the parameters, and report confidence intervals. For this, we will use a public dataset. We'll use the iris dataset again and perform random sampling and compute estimates and intervals. So let's start with this. I'm going to create a new file, exactly same as this, just the second exercise. Get my URL for iris, and then first import pandas as PD for my data frame. From my distributions, I'm going to use scipy or skippy.stats import for normal distribution. I'm going to use norm and import numpy as np. Okay, so that's good. So first thing is loading the data set. So I'm going to say pound load iris data set, that is URL, this URL. So using create a data frame using pandas. So I'm going to say pd dot read csv and pass the URL to this. Perfect. Next, let's do sampling of the data. So let's say sample equal to df. We'll use same thing that we used before, sepal length from the data set. You can open it and check it out or use something else if you want. Sample 30 random state equal to 42. So every time it gives me the same data set. So that's why I'm setting the seed this time. Next, I am going to say sample statistics. So I'll use the same that we did in the previous one where get the mean. I'll say sample dot mean, straightforward. Next, I'll say standard deviation equal to sample dot std. Next, we want to get the length of this data set of this sample. So I'm going to say length of sample. Perfect. Now these are data frames, so you can directly call these functions on a data frame. Next, I am going to go ahead and get the confidence interval. For that, first, as we've done before, z value equal to norm dot ppf of 0.975. I'll set just that for this. This is z score of 95%. Margin of error equal to z value times standard deviation divided by np dot square root of n. Perfect. Now I have my ci equal to mean minus margin of error, comma, mean plus margin of error. So this will be my range of my ci. Let's print this out. Let's get the sample mean first, and that is my mean. And then let's get the 95% confidence interval, which is ci. So hope you were able to get the expected output for this. It will be a report with sample mean, confidence interval for the mean, and the interpretation of the results. So let's go back and clear it out. I'll have Python exercise 2, and there you go. Our sample mean is 5.98, and the confidence level interval is 5.67 to 6.2. So the sepal length is in between 5 to 6 levels. So that's perfect. That's awesome. We used the real life data, so that's awesome. If you had any questions or problems while doing this, let me know and I can help you out in the comments. And for additional practice, you can try to create the confidence intervals for other statistics. Example, variance. Try the variance. We've done this previously in our previous videos. So just to recollect that, you can try this. You can perform stratified sampling and compare intervals across strata. So you can try that. And you can also try to visualize confidence intervals for multiple samplings using matplotlib. So just to summarize, today we delved into statistical inference concepts, focusing on point and interval estimation. By calculating the confidence intervals and conducting sampling, we developed practical skills for analyzing and interpreting data in machine learning. This will be very helpful for us in future. So hope you were able to follow along and let me know if you had any troubles. Day 4. Hypothesis testing and p-values. Today we'll start with Introduction to Hypothesis Testing. Now, what is hypothesis testing? A statistical method to determine if there is enough evidence in a sample to infer a conclusion about the population. That's what hypothesis testing is. Some of the key components include null hypothesis, which assumes no effect or no difference, which is also represented as H of O. Examples can be the mean test score of two groups is the same. Next, we have alternative hypothesis, which is represented as H of A, which indicates an effect or difference. Example is the mean test score of two groups is different. Now, what are the steps in hypothesis testing? First, you need to formulate HO and HA, which are null hypothesis and alternative hypothesis. Then you need to choose a significance level alpha, which common values are 0.05 or 0.01. Next step is to calculate the test statistics, which is either t statistics or z statistic. Then you determine the p-value, followed by compare the p-value to alpha, where if p is less than equal to alpha, then you reject the null hypothesis. But if p is greater than alpha, then fail to reject the null hypothesis. Next, let's look at understanding the p-values and significance levels. The p-value is the probability of observing results as extreme as the test statistics under null hypothesis. Smaller p-values indicate a stronger evidence against null hypothesis. Then we have the significance levels, alpha, where threshold for deciding whether to reject a null hypothesis. Then example can be alpha is 0.05, means a 5% risk of rejecting null hypothesis when it is true. Also, we have decision rule, which talks about reject the null hypothesis if p is less than equal to alpha, fail to reject null hypothesis if p is greater than alpha. Now, what are the different types of errors? We have type 1 error alpha with incorrectly incorrectly rejecting null hypothesis when it is true. Example can be concluding a drug is effective when it's not. We have type 2 error, which is beta, which is failing to reject null hypothesis when it is false. Example can be concluding a drug is not effective when it is actually effective. Let's look at some of the examples in a tabular format. We have reality on the left side, we have decision in the middle, and conclusion at the end. Now, null hypothesis is true for the first case. We reject the null hypothesis, and it's a type 1 error because the null hypothesis is true, but we are rejecting it. Next one is null hypothesis is true, and we fail to reject null hypothesis, which is correct. All good in this case. Null hypothesis is false, and we are rejecting null hypothesis, which is correct. And finally, null hypothesis is false, but we fail to reject the null hypothesis. That's a type 2 error, where, as I mentioned in the example, concluding a drug is not effective when it is actually effective. Next, let's do some hands-on exercise based on what we have learned. So first, let's perform a hypothesis test. The objective here is to perform a one sample t-test to test if the mean of a data set differs from a known value. So let's do this in Python. So I'm going to open my editor and I'm going to say Python file, save it as day 4 underscore exercise 1.py. Here first let's import numpy as np, then we'll need scipy dot stats, we'll import tt test 1 samp, and we'll get some sample data or set up some sample data by saying data equal to 12, 14, 15, 16, 17, 18, one more, let's say 19. So I have my sample data set up. Let's do null hypothesis with mean equal to, let's say 15, based on the data that we have above. I'm going to say population underscore mean equal to 15. Now let's perform the t-test. For this, I'm going to say t-stat and p-value, that's what we want, equal to t-test 1 samp, and give it the parameter that it needs is the data and the population mean, which I have, so I'm going to provide those, and let's print these values. T statistic is comma t underscore stat. Next I want to display the p-value, and that is p underscore value. Now let's do our interpret the results. Interpret the results. To interpret the result, as I mentioned, we'll compare it with alpha, where alpha equal to 0.05. Now if p-value is less than equal to alpha, if you remember the rule, what we're going to do in this case is reject the null hypothesis because of significant difference, else we will fail to reject the null hypothesis because there is no significant difference. So let's see which one is true in this case. I'm going to open this, say Python day 4 exercise 1, run it, and it says fail to reject null hypothesis. The t-stat is 0.94 and p-value is 0.3. If you see 0.3 is it less than greater than? No, it's more. So that's why it failed to reject the null hypothesis because of no significant difference. Now let's jump into exercise 2. Our exercise 2 is two sample t-test. The objective here is to compare means of two groups. Example, test score of two different classes. So let's go ahead and create a new file, day 4 exercise 2. In here, from scipy dot stats import t-test, not this one, individual. I am gonna say data from two classes or groups of their scores. Group 1 has, use the same one that we use, 0, 12, 14, 15, 16, 18, and 19. The group 2 has data which is 11, 13, 14, 15, 16, 17, 12, 13, 14, 15, 16, 17. Let's use one more, 18. I like to use even numbers, 12, 14, 15, 16, 17 also, 18 and 19. Perfect. Now let's perform the t-test on this. Perform t-test, where we will get first the t-stat, same as before, comma p underscore value equal to tt in from here, and we'll pass group 1 and group 2 as the parameters. So that will give me my t statistic and p value. So I am going to print those out. I'm going to say t statistic is comma t stat, and the other thing, p value is p dash value is p value. So I have that. Let's do the interpretation of the results, where I am setting alpha again as 0.05. In this case, I'll check if p value is less than equal to alpha. I will say, what do? In this case, same as before, I'll reject the null hypothesis because there is significant difference. Else, I will fail to reject the null hypothesis because there is no significant difference. Let's run through this, clear it out. Number 2, the t statistic is 0.7, p value is 0.45, higher than the previous one, which means it will fail to reject the null hypothesis because there is no significant difference here. So that kind of concludes our 2 exercises. I hope you were able to follow along or do these. If not, let me know in the comments and I'll get back to you. For additional practice, we will be perform a z-test for large sample size. Try that out. Next, use the iris dataset to test if the mean sepal length differs between two different species, because we have multiple species in there. And then perform hypothesis testing on proportions using the binomial distribution. Try that out and let me know how it goes. So just to summarize, today we learned to perform hypothesis testing, interpret the p-values, and understand error types. By conducting these t-tests and interpreting results, we developed critical skills for evaluating statistical evidence in machine learning and data science. I hope it was helpful. If you have any questions, do let me know. Day 5, types of hypothesis tests. Today we're going to look at different tests, and we're going to start with t-tests. The purpose of t-test is to test whether the means of one or more groups differ significantly. There are different types. The types that we're going to talk about here is, first is one sample t-test. This tests if the mean of a sample differs from a known value or a population mean. Then we have two sample t-test, which is also called as independent t-test, which compares the means of two independent groups. We also have paired sample t-test. This compares means of two related groups, example pre-test versus post-test. Let's look at some example use cases. one sample is testing if the average test score of a class differs from the national average. We can use two samples for comparing test scores between two different classes. We also can use paired sample for comparing weight before and after a diet program. Let's talk about another test, which is chi-square test. The purpose of chi-square test is to test for independence of goodness of fit in categorical data. The chi-square test of independence tests if two categorical variables are independent. Example use case is testing if gender is independent of preference for a particular product. The steps that we follow here is first we create a contingency table, then we calculate the expected frequencies, and finally we compute the x square statistics and p-value. We can do this in Python. Let's go ahead and quickly start a new file, Python file. I'll save it in my day 5, call it day 5 underscore sample. And here first from scipy dot stats, I will import the library that is, or the function that is chi2 underscore contingency. Now, as I mentioned, first let's create a contingency table. So contingency table. I am going to create a data table. Now it's a table of 2 by 2. So I am going to say 50 comma 30, and the second set will be 20 comma 40. Now here next is let's perform chi square test. Now having that function makes it much more easier. The function which is chi2 underscore contingency, and pass it data. Now this particular function will give us back 4 different things. First it will give us the chi2, next it will give us the p-value, the DOF, and expected value. So this is what we get from this particular function. Now let's print all these things. The first one, chi2, which is the chi square statistic, is chi2. Next, the p-value is p dash value. Let's print that out as p. We don't care about DOF, but we care about the expected frequencies. So I am gonna say expected frequencies is expected. Now this can be this is a matrix, so I'm gonna do /n, so it goes in the next line. Save it and let's run this. Python day 5 underscore samples.py, and there you go. We have our chi-square statistics, which is 10 based on the data that we have. P-value is 0.001. Expected frequencies are 40, 40, 30, 30. Perfect. So that's how you can do a chi-square test. Next, let's look at ANOVA, or analysis of variance. The purpose for this is to compare the means of 3 or more groups. For hypothesis, we use the null hypothesis, which is all groups means are equal, and alternative hypothesis, where at least one group mean is different. The example use case for this is testing if the mean scores of students from 3 different schools differ. So let's go ahead and look at the Python implementation for this. So I am going to use the same one. I am going to leave some of it. I will need f underscore from my same stats. I'll need f underscore one way. That's what we would need for our ANOVA. And now first, let's get data for 3 groups. As I mentioned, since we'll be testing 3 groups, I'm going to create a group 1 equal to, and the values here is 12, 14, 15, 16, and 17. For group 2 and group 3, I'll have some different datas. Group 2, I will create 11, 13, 14, 15, 16, and for group 3, Let me randomize it again based on my randomizer. 10, 12, 13, 14, 15. I'm just putting any numbers that come to my head. Now, next is to perform ANOVA. To do that, what I'm going to do is I'm going to call that f underscore one way function and pass it group 1, group 2, and group 3. And this will give me f underscore stat, which is f statistic, and p value, p underscore value equal to this. So let's print these out. F statistic, which is f underscore stat, and I will print the p value, which is p underscore value. Perfect. Let's run this. Clear. And there you go. We have f statistic of 1.35 and p value of 0.29. So this is how you can do analysis of variance or ANOVA tests. Next, now that we have everything in place, let's go and do some hands-on exercises. Our first exercise is to conduct t-test. Our second will be to perform a chi-square test, and the third exercise is to conduct ANOVA. Now, if you want to follow along, we can probably follow this particular exercises. So first, let's go ahead and clear this out. I'm going to create my first exercise, call it day 5 underscore ex1 dot py. And here, as I mentioned, the first thing that we will be doing is conducting t-test. So I am going to say conduct t-test, and the objective here is to perform one sample, two sample, and paired t-tests. That's what we will be doing here. So if you want to get more idea on that, I'm going to say perform one sample, and then I said two sample, and we'll also do the paired t-test. So these are the different tests we'll do. So first one is, let's say, one sample t-test. Next we'll do two sample t-test, and next we'll do paired t-test. So we have these three different things that we will be doing. So let's start first with importing some libraries. So I'm going to say for modules, scipy dot stats, I will be importing all these tests. So tt test one sample, tt test I want individual, and then tt test rel. So these are the different modules or functions that we need. So data, let's set up the data first. I'll say 12, 14, 15, 16, 17. So this will be my data set for my one sample t-test. I will also need something. So if I run the t-test one sample, the things that it needs is we need three different, as you can see here, we need different parameters. First is we need the data. So I'm going to say data is what my parameter is, and then we need to give a population mean. So I will create population underscore mean. So just by looking at the data up above here, I'm going to say population mean is 15. That's what I provided here. Now this particular test will give us the t-stat and will give us p-value. So let's print those out. I can just say print one sample t test gives me, oops, we get t-stat and we get p-value. So that's what I'm going to print out. Now for my two sample t-test, I'm going to need two groups. So I'm going to say group 1 equal to, I can take the same value from here, and then I'm going to say group 2. I can even use the data variable, but it's better to always name your variables properly. So that's why I'm using the same one. 11, 13, 14, 15, and 16 is the values that I'll use. and this time I'm going to call t-test t-test ind, and here I'm going to pass group 1 data and group 2 data. Now this will give back t underscore stat p underscore value, so that will be assigned to this. So now let's print our 2 sample t test, and this will give us comma t underscore stat and p underscore value. So that's my 2 sample test. Now for our pair test, for this we would need 2 set of data, pre underscore test, pre data and post data. So I'm going to use the same data that we have here, 12, 14, 15, and then I'll say post underscore test equal to, for this I will give 13, 14, 16, 17, and 18. So almost same, but a little bit more than the pre-test. So I'm going to say t underscore stat, because we will get these two values, p value, when we call the function t-test underscore rel, and it needs pre-test and post-test data. And I am going to say print paired t-test is t underscore stat, comma, p underscore value. So save it. So we have completed our 1 sample t-test, 2 sample t-test, and paired t-test. Let me save it. Go back here and say Python day5 ex1.py, and these are the results of our 1 sample t-test, 2 sample t-test, and paired t-test based on the data that we have provided. Perfect. So we have that. The next exercise is, as we mentioned, is to do the perform a chi-square test. So we already done something similar chi-square test earlier. So I am going to try to breeze through this, save, and as I mentioned, this is perform a chi-square test. In here, the objective is to test the independence of 2 categorical variables. So from scipy dot stats import chi underscore, or sorry, chi2. I guess that's why it was not giving me chi2 underscore contingency. Now first, as you know, we need to create a contingency table. So make sure your contingency table is available. I am going to create again a 3x3, this 3x2 this time data set. So the first one will have 50, 30, and 20. My second row in the matrix will have 30, 40, and 30 as the values. So my data is available. Now let's go ahead and perform the chi-square test. To do that, I will call chi underscore to contingency, and all it needs is our data. So I'll pass that. Now this will give us back chi2, comma, p-value, comma, DOF, comma, expected. This is what will come back from this function. Now I am going to print all of them one out of another. You can do the same thing with your data set. Square statistic is chi2. Next, let's do that for the p-values, which is p underscore, or just p for this particular case. And next, finally, we'll print the expected frequencies, which is in matrix. So I'm going to say /n and say expected, so it shows up in the next line. Let's go ahead and run this Python day5 ex2.py, and there you go. We have our chi-square statistics 8.4, p-values is 0.01, and expected frequencies are listed right here as a 3x2 matrix, 40, 35, 25, and 40, 35, 25 based on the input that we have provided. Now finally, the last exercise is to conduct an ANOVA. Now for that we need F1 way. So I'm going to save this file as new file as 3.py. Here, first I will say from scipy dot stats, I want to import f underscore one way, and then let's get the data for three groups. For that, I'll say group 1 equal to 10, 12, 14, 16, and 18. Next one, I'll create another group, group 2 equal to, start with single digits, 9, 11, 13, 15, and 17. And group 3 equal to 8, 10, 12, 14, and 16. So I have my three groups. Now let's go ahead and perform ANOVA, which is f underscore one way, and it needs the three groups, group 1, group 2, and group 3. So I have that. This will give me back my fstat and p-value, my f statistics and my p-value for this, which I can print it out saying the value of my f statistic is comma f underscore stat, and my print, my p-value is p underscore value. So let's go ahead and run this, clear this out, and I am going to say I want to run, and we have our f statistics and our p-value for the data for three groups that we have provided. So we've done all the three of them. We conducted the t-test, we performed the chi-square test, and we did our ANOVA here. So our next, for additional practice, you can try out to perform a two-way ANOVA to test for interaction effects. Also, you can try to use real world data sets, example, student scores by gender and class for hypothesis testing. You can find these data sets online, or if you are in a school or affiliated with a school, you can get data set from there. And finally, you can visualize these test results using box plots or bar plots. To summarize, today we explored various hypothesis tests, including the t-test, chi-square test, and ANOVA. By conducting these tests and interpreting the results, we gained a comprehensive understanding of statistical testing in data science and machine learning. If you had any issues or problems, let me know. If you have any suggestions, recommendations, please message me and I'll get back to you. Day 6, Correlation and Regression Analysis. Today, we're going to look at understanding correlation. Now, what is correlation? Correlation measures the strength and direction of the relationship between two variables. The values range from -1, which is a perfect negative correlation, to 1, which is a perfect positive correlation, with 0 indicating no correlation. Now, the different types of correlations include the Pearson correlation coefficient, or represented by R, which measures linear relationships. And it assumes data is normally distributed and relationships are linear. Then we have the Spearman correlation coefficient P. It measures monotonic relationships and based on rank orders of data. And it is useful for non-linear relationships. Let's look at an example of this in Python. So I'm going to start with a new file, save it as day 6 underscore samples sp.py, and here first let's import numpy because it has some of the libraries available or functions available, and then from scipy dot stats import Pearson and Spearman. Okay, so these are the two things that we need. Now first, x equal to np dot array. Let's create a data set which is a list of 1, 2, 3, 4, and 5 items, and then let's create another one which is y, which is set of, let's increment it a little bit, 2, 4, 6, 8, and 10. Already see probably a correlation between the two data sets, but let's first look for use Pearson correlation of how you use it. So the way to use it is we can just call that Pearson R and pass it x and y, and this will give us R comma, the next one we don't care about, underscore, because it gives us this particular function Pearsoner. If you next, let's go ahead and print Pearson correlation coefficient, and that is R. Next, let's do the Spearman correlation, and for that I'll use the other function that we have imported, Spearman R, pass it x and y, and this will give me RHO comma underscore. These are two variables that I'm saving data in. Say print Spearman correlation coefficient, which I have saved in RHO. So let's print out Pearson and Spearman correlation for the data set that we have. So I'm going to go ahead and say Python day6.underscore samples.py, and our Pearson correlation is 1.0 and Spearman correlation coefficient is 0.99, which is also close to 1.0. So they are correlated very closely. That's what these coefficients are telling us. Next, let's look at linear regression basics. Now, what is linear regression? It is a method to model the relationship between a dependent variable y and one or more independent variables x. The formula for simple linear regression is y equal to b of 0 plus b1x plus e, where b0 is the intercept, b1 is the slope, which indicates the change in y for a 1 unit change in x, and e is the error term. Now, some of the key metrics that we have here is slope, which is beta1 or b1, describes the strength and direction of the relationship. The intercept, b of 0, the predicted value of y when x equal to 0. And we have r squared, which I've used before, which measures the proportion of variance in y explained by x. The formula for that is r square equal to 1 minus ss res divided by ss total, and that we can probably play around in Python. So I'm going to use this, and first from sklearn dot linear model import linear regression, and then from we also need numpy as np. Now let's create some sample data. This is where np.array comes into picture, where we'll create 1 2 3 4 5. I can just reshape it in the order of -1 comma 1, and this will give me the data set for x, and for y I am going to say np.array, and here I'll take the data as 2 4 5 8 and 10. Now let's fit the linear regression by model equal to linear regression. This is how we create an instance of the model, and then I fit and give it data x and y. So this will help us get the slope, intercept, and r squared. So to do that, I can say print slope is model dot coefficients of 0. That will give me the slope. For my intercept, I can say model underscore dot intercept underscore, and for finally r squared, I can say model dot score and pass it x comma y. So this will give me the r score for this. Close it. Perfect. Now let's run this and get our slope, intercept, and r square. So I'm going to clear this, run it again, and it'll take some time, and there we go. We have a slope of 2,
intercept of minus 0.2 and r squared is 0.98. So that's pretty good. So we have our data based on that. We have the values based on this data that we have, and we have used the linear regression model here. Next, let's look at interpreting the regression results. Now, slope that we got first, the slope b1, or in this case, it's 2.0.001, indicates the magnitude and direction of the relationship. If you look at the data here, 1 to 2, 2 to 4, 3 to 5, 4 to 8, and 5 to 10, that gives me a slope of 2 based on the basic math that I know of. Similarly, for intercept is the starting point of the regression line. So that's why it's minus 0.2. And we have r squared, which closer to 1 indicates a better fit. So since we have 0.98, which means it's a better fit for this particular model, and that's why r squared is closer to 1. Next, let's look at some hands-on exercises. Our first exercise is to calculate correlation between features. The objective here is to compute and visualize correlations in a particular data set. And for this, we are going to use the iris data set. So we are going to load that iris data set that we've used before. And then we are going to calculate the Pearson correlation between the numerical features. And then finally, we'll visualize the correlation using a heat map. So let's get started. To clear this out, create a new file, save it as day6 underscore ex1.py. And here, let's start with importing pandas since we are going to use a data set, pd. Then since we are going to do a heat map, let's import seaborn as SNS. And since we are going to plot it, we would need matplotlib pyplot as plt. Perfect. So I have my libraries that I need perfect in here. Next, let's load so first step, as I mentioned, is to load the iris data set. Now that I'll load it from a URL and put it in a data frame. For that, I'll say pd.readcsv and pass the URL to it. Next, let's compute the correlation matrix for this. To do that, I can say correlation underscore matrix. It's a variable, so it doesn't matter if I do a typo as long as I'm using the same thing over and over again. df dot give me the correlation. Now based on that correlation, let's plot a heat map. So for that, I'm going to say sns dot heat map. I'm going to pass the correlation matrix. I will say annotate equal to true, and cmap, the colors that I want to use is cool warm. There's a bunch of different options, but I'm going to select cool warm for this. Next, let's give a title to this plot, and the title I'll call it feature correlations. And finally, let's show this plot. Perfect. So now let's go here. I've already cleared it. Python day6 underscore ex1.py. Let's run it. Looks like it didn't like our species data. So what I'm going to do is, so if you look at this data set here, I'm going to open this in Chrome, and we have this species column which is text, and it doesn't like that. So usually what I do is I just drop that. So what I'm going to do here is, before I do the correlation, I am going to say df dot, or give the name of the column and drop the species column from it. And let's run it again. I'm going to clear this out. And there you go. We have our correlation matrix here between sepal length, sepal width, petal length, petal width, and it's the other ways. On the y-axis, we have the same thing, and it has correlationship between them. So we can see the correlation with the data set that we have. So that's our exercise 1. Our exercise 2 is to fit a simple linear regression model. So the objective here is to fit a regression model to sample data and interpret the coefficients. We will generate some random data or use a real data set and then fit a linear regression model and interpret the slope, intercept, and r square. So for this, we're going to just generate some data for our sample. So I am going to close this, clear it out, create a new project, call it day6 exercise 2.py. Here, let's start with NumPy. It will be useful for creating data, generating data. Next, we want to use linear regression. So from sklearn dot linear model, I will import linear regression, and then I will import matplotlib dot py plot as plt to plot the data, to visualize the data. So first step, generate the data. For that, I'm going to say np dot random dot seed 42. The reason I'm setting the seed is just so that next time I'm calling this random method, I need the same data that I get this time. So I'm going to say x equal to np dot random dot rand 100 comma 1 times, let's multiply it with 10 just for the fun of it, y equal to 3 times x plus np dot random dot randn 100 comma 1 times 2. The reason I use rand on rand n is because we have set up a seed, or else it will get me the same data set for both of them. So next, let's go ahead and fit a linear regression. Fit linear regression here. For that, I'll say model equal to linear regression. Next, I'm going to say model dot fit to fit the model, and I'll pass x and y values to it. Next is to get the coefficients. So I'll say get coefficients, and the coefficients that I need is first is slope, then is intercept and r square. So I'm going to say slope equal to model and dot coefficients 0 of 0. Next is my intercept, that is model dot intercept of 0, and then my r squared equal to model dot score of x comma y. So that will give me my data. So now let's visualize these results. I don't want to print them, I want to visualize. So that's why I have matplotlib. So plot dot create a scatter plot for this x comma y. Color for these scatters I'll use blue, and for a label I'll use data. Straightforward. plt dot plot this data, where I'll pass x, and then I'll say model dot predicted values of x, give a color of red for these, and my label equal to regression line. So it will give me the two different scatters and the plot for blue color for scatters and plot with red. So you can see the difference. Plot dot legend. What do you want to show? Let's show a title. Title, we'll call it linear regression, and finally display this particular plot. So we did all the different things. We fit the linear regression, we got the coefficients, and visualize the result. The expected output for this should be, we should see the slope, intercept, and R2, and scatter plot with the regression line. So let's go ahead and run it. Day 6 ex2.py, and here is my regression line and my scatter plot displayed around the regression line. As you can see, since we're using the regression model, the scatter is right around the regression line, which shows a good data set that we have created here. Next, for additional practice, you can fit a multilinear regression model with multiple independent variables. You can next compare the correlation and regression results for non-linear relationships. Try that out. That's an interesting one. And you can use real-world data sets, example housing prices, for regression analysis. So you can get all these data from online, play with them, and let me know how it goes. If you have any issues or problems, let me know and I can help you out. So just to summarize, today we explored the concepts of correlation and regression, focusing on interpreting relationships between variables. By calculating correlations and fitting regression models, we gained essential skills for predictive analysis in machine learning. I hope it was helpful. If you have any questions, let me know and I'll get back to you. Day 7, Statistical Analysis Project, Analyzing Real World Data. So today we will start with first understanding applying probability and statistical concepts. So whatever we have learned till now, we can use all these previously learned statistics methods to draw meaningful insights from real world data. What we will be doing is we'll be applying probability concepts to understand distributions. We'll do hypothesis testing to identify significant relationships or differences. And we're going to use regression analysis to explore and quantify relationships between variables. So, to start with, let's look at performing exploratory data analysis or EDA. The steps in EDA, if you remember, is first to load and inspect the dataset. Next, we check for missing or inconsistent data. And step number 3 is to visualize these distributions and relationships using histograms, scatter plots, and correlation heat maps. You can also create a report after that to send to your data scientist. The key goals here is to understand the data structure and identify patterns, trends, and outliers. We will be using a data set called as the tips data set for this. We can look at an example code here. So I'm going to create a new file, Python file, save it in my day 7, call it day 7 underscore project. And this is the URL that we'll be using, github usercontent.com/mwaskom/cbond data master tips.csv. This is where we will get our data from. So to start with, let's go ahead and import pandas as pd, import cbond as sns, and next I will import matplotlib.pyplot as plt, something that we have done quite a lot. First step is to load the data set. Now we already have the URL, so that's what we are going to use. Then we are going to move that to a data frame by reading that data using read CSV method from this URL. Next, as I mentioned, let's inspect the data. To do that, I can print a little bit of the data or information about the data by saying df.info. It will tell me about the columns. I can also get some statistics by saying df.describe. So once I have that, finally, let's go ahead and visualize the distributions. I can do that by saying visualize distributions sns.histplot, and to this I will pass inside here. If you look at my data set, let's copy this, let's open this data set in Chrome. If you look at the data set, we have total bill, tip, sex, smoker, day, time, and size. So I'll go back here, and here I will take the total bill column to plot it. So I'm going to say total bill, and then I'll set the KDE to be true. There you go, perfect. Next, I'm going to give a title. In this title, I'll say distribution of total bill, and let's display this plot. There you go, perfect. If you want to look at the correlation heat map, what I'm going to do is sns dot heat map pass df dot correlation annotate equal to true, and cmap equal to, we'll use the same favorite one, cool warm, plt dot plot dot title will give a title of correlation heat map, and then plt dot show. So two different plots, one for this. And so I'm going to comment this out first. So let's look at the visualize the distributions. I'm going to go here and I am going to say Python day7.project, run it, take the data, and it will show me the distribution of the total bill depending on that. So perfect. So that, and also gives me the information, and because we said that we'll inspect the data information and the total bill, where it shows the total bill distribution, the tip, the size. It will give me, so there's 244 elements. The mean is this much. What is the total tip mean, the size of the mean, a standard deviation, minimum, maximum. So these parameters are there. Perfect. And close this, go back and comment this time, and look at the correlation heat map. Clear it out, run it one more time. So looks like I have some error here, could not convert string to float female, because the correlation has, as you can see, bunch of, not just the bill and the tip, it also has all these things. So I need to drop those things out. So if you remember from before, the way to drop non float characters is non-float columns is to say, let's say delete df. From that we'll drop sex. We can drop smoker is yes or no, so we'll drop that also. Next day, let's drop that. Do we need to drop anything? Time is dinner, so I'm going to drop that too. And the last one is size, so I can keep that one. Save this. Where do you go? Okay, save it, go back, clear it out, and run it again. And there you go. We have a correlation between size, tip, and total bill right here displayed nicely. So that kind of shows you how you can perform EDA and visualize data here. So next is conducting the hypothesis testing. So here the steps that will follow is, first we will formulate null and alternative hypothesis, which is H0 and HA, and then choose and perform an appropriate hypothesis test. Example, we can do the t-test, or we can do the chi-square test, or both. And finally, we'll interpret the p-values and the test results. So let's go ahead and start that. I'm going to use the same one. I am going to comment out everything here and run stuff at the bottom. From scipy.stats, I am going to import t-test, and I'm going to use this one because there'll be two groups. Now we'll separate the data by gender. So we have the entire data here, so I would need this data frame. So I will still keep my pandas, load my data set, and have my data set available for this. And I will say, let's go ahead and separate data by gender. So we have male and female over there, so these are two options. So separate that data, and that is what we can use the test for. I'll say male tips equal to df of df sex, in this case equal to male. And so I will take male, and then from there I'll take the tip of it, tip. And similarly for female tips, df sex equal to female, and take the tip from it. So that will give me male tips and female tips in two different parameters. Now I can perform my t-test on this. To do that, I can, from this t-test, I get t-stat with t-statistics, and we get the p-value. So for that, I'll call that function, and we'll pass male tips and female tips. So now first let's print the t statistic for t underscore stat, and we'll print the p value, and that is p underscore value. Now to interpret these results, let's say interpret results, I need to use some alpha For alpha, I will use the standard one 0.05, where I can say if p underscore value is less than equal to alpha, then print reject all null hypothesis. Why are we rejecting the null hypothesis? Because there is significant difference. So we are trying to see if there's a significant difference between male and female tips. No significant difference. Fail to reject. So let's see if there is a significant difference or not. So I am going to go ahead and first of all, let's close this, clear it out, and now I can run this Python day 7 project. It says fail to reject all, there's no significant difference. So based on the p-value, I don't think there's any significant difference between the data that we have as compared to male tips and female tips. Next is to applying linear regression. The steps that we'll follow here include: first, we will select the dependent and independent variables. We'll fit a regression model to the data and interpret the coefficients and the R-square value. So the example we will be doing is analyzing the relationship between total bill and the tip. So I'm going to go ahead and start with the same code base that we have. I don't need any of these anymore, I think. I need the data set, so I'm going to keep this still uncommented, but I would need my, since I'm going to implement linear regression from linear model, I will import linear regression, and I will also use NumPy because of the array operations. So I have my URL data. Now first, let's go ahead and define the variables. So to define the variables, we need x and y. For x, we will say df total underscore bill. We'll use the total bill column. I say values, take the values from that and reshape it to -1, 1. Next, for y, I will take the tip values. So I'm doing a regression between the total bill versus the tip that was paid. Tip dot values. There's always a linear regression between these, so it's an easy problem to solve. Linear regression. Let's say model equal to linear regression model dot fit x comma y. Now let's output the coefficients. Now to output the coefficients, we'll say print the three coefficients that we have is slope, intercept, and R-shape. That's what we have covered this week. So I'll say first start with slope is by saying model dot coefficient of 0. Next, we need the intercept that we can get from model dot intercept. Perfect. And then we need the R squared, which we can get from model dot score and pass it x and y as we learned earlier. So that will give us our coefficients. Now let's plot the regression. So to plot that, I'm going to say SNS dot scatter plot x equal to df of, we'll pick total bill underscore bill, and then for y we'll use df of tip. So we can see if the tips lie across the regression line. Color equal to blue, and next we'll say plot dot plt dot plot df to total underscore. Oops, it's always good to sometimes just copy paste so you don't do typos. With the model dot predict, and I'll pass it the prediction values. I'll say color equal to red. So this will kind of tell you if your servers are happy with the bills that they predicted that they'll get versus not. Regression line, of course, this is just the system plotting it out for you, not the real tips, but still, as a server, you would always expect more. Versus tip plt dot legend and plt dot show. So now looks like I don't have my libraries here. So I am going to uncomment these two because I'm using them here. So perfect. So this should do our, this is how we apply the linear regression. So let's run it and check it out. I'm going to clear it out and run the same project. It's going to give me my slope, my intercept, my r squared, and here is my total. It's kind of shows the regression line, whereas the tips that were paid, if you see, some of them were very high, which is pretty good, and most of them are up, so that means it's a pretty good restaurant and the servers are doing pretty good job. But this is our entire flow here of total bill versus tip in linear regression application. Next, so let's dive into our hands-on project, which is on statistical analysis of real-world data. We already did a bunch of this, but the project task here is first to perform exploratory data analysis, which is the EDA, where we'll inspect the data set structure and summarize key features, visualize distributions, relationships, and correlations. We'll use that tips data set that we used, and we will plot and visualize the relationships. Next is to conduct hypothesis test, where we will be comparing tips by gender, is t-test, and this test for independence between smoking status and time of the day, which is we'll use t-square test, and we're going to code that part. Next, we will apply linear regression to that. We'll analyze the relationship between total bill and tip and interpret the slope, intercept, and r square. Visualize the regression line on a scatter plot. So to start off, let's go ahead and perform an exploratory data analysis on our data set. So I'm going to start with my project. I am going to make sure that I close all these things. Close this, clear, and I have my data set right here. And I'm going to use some of the code here. So I'm going to say save as day 7 underscore exercise dot py, since we have only one exercise. And I'm going to paste it here. Now, the first step is to do the EDA for this data set that we have. So for that, we need pandas. I'm going to remove some of the things. We don't need this. We don't need NumPy. We need Seaborn and as SNS and Matplotlib. We'll load the data set here. First, as a part of the EDA, we need to inspect the data. So I'm going to uncomment this, where I'm going to get the information and then describe this. Again, some of the things are not required here, which are these items in the data frame, because they have text in there. So I'm going to remove that for this EDA. Visualize the distributions here. I'm going to comment this, uncomment these out, and then finally we'll display the heat map. So this is the first step, which is perform EDA data analysis. So that's what we need to do for this exercise. I'm going to go ahead and then run this Python day 7 underscore exercise and run it. And this is our EDA analysis, where it shows the information, it describes the data that we have, and also we visualized the data here in a graph. So that's perfect. And here is our heat map, which shows the heat map for that data. So that's done. I'm going to clear it out. Of course, it gave me an error because of these lines, which are still not commented out. So I'm going to comment them out. So next step is to conduct hypothesis test, and inside our hypothesis test, as I mentioned, we'll compare tips by gender, and then we'll test for independence between smoking status and time of the day, which is t-square test. So we have some of that, but I am going to go ahead and comment some of these things that we did for EDA. And next, I need something from the scipy dot stats import, I need the chi2 underscore contingency, and then I need to create a contingency table. Now my contingency table is contingency table comes from my dataset pd dot cross tab, use that function and get df of smoker and df of the time. So this will give me a cross tab between these two parameters. Next, let's go ahead and perform. I'm going to comment and say perform the chi square test here. Now the chi square test is using that function where it will need the contingency table. So I'll pass that, and this will give me chi2. It will give me the p-value and other stuff which I don't need, which is DOF and expected. So those will come back from this particular function. Let's print them out. Print chi square statistic, and I'm going to say chi2. Next, I want the p-value, p dash value, which is p. Now to interpret the results based on these tests, interpret the result, I am going to say if p is less than equal to alpha, and alpha will use the standard 0.05, then I will say print reject the null hypothesis because variables are dependent. Whereas if it's not, then I'll say, let's get rid of this, fail to reject because variables are independent. So this will help us tell us if the variables are dependent or independent. So let's go ahead and run this. It will run through it and it will give me my chi square and my p-value. Looks like variables are independent, so it doesn't matter when if there's a smoker or not, depending on what time they are working or not. So that's good. And finally, our final is to apply a linear regression, which we already done that here. If you look at our final right around here, we get the coefficients, we apply linear regression to the data, we got slope, intercept, and r squared, and we visualize the data for linear regression. So that's what you'll have to do. Make sure that this works. I also need this for it, and I would not need any of these anymore. So this will be your linear regression test. So let me know if you are able to get the same output as I do. If not, let me know in the comments. But this kind of ends our day 7 on week 4, where we have done a bunch of different things, and most of the deliverables from this projects are: we did the exploratory data analysis report, where include visualizations and summaries of data distribution and relationship. We did hypothesis test results, which clearly states hypothesis test statistics, p-values, and conclusions. And linear regression results we saw, which presents regression coefficients, r square, and interpretation of the relationship. And we can create a comprehensive report out of this, which summarizes the insights and findings in a clear and concise manner, which can be provided to your business partners, and they can take proper step based on that data that you have provided. Now, for additional practice, if you want, you can extend the project by exploring additional relationships. Example, day of the week versus tip amount. You can perform multiple linear regression with additional variables. Example include the smoking status, and you can also use another real world data set like healthcare or sales data to apply similar techniques. So try to find some data set and play around and get as much practice as possible before we get into machine learning next week. So just to recap, this week and especially today, we integrated our knowledge of probability, hypothesis testing, and regression to analyze the real world data sets. And by performing EDA, conducting hypothesis test, and applying the regression analysis, we gained practical experience in statistical analysis and its application in data driven decision making. So, if this was helpful, let me know. If not, let me know again in the messages. And if you have any problems or issues, again, let me know in my messages and I'll get back to you.